In the last couple of videos, we did some work to define vectors a little more carefully and to develop vector arithmetic. Now going forward, what I'd like to do is revisit the kinematics that we were doing in one dimension, but now extend it to 2 dimensions. So to that end, we're going to extend our definitions of position, velocity, and acceleration from 1 to 2 dimensions. You could extend to 3D if you need to, but it usually turns out that any motion you have will be in 3D will actually be in a plane. And so you can usually put it into 2D unless you're working in a non-inertial frame, which is beyond the scope of what we're doing here. So anyway, we'll start by defining position. So the name of the position vector is r. The name of the x component of the position vector is just x. So we would take the x component and multiply that by I hat, the unit vector that points in the plus x direction. And we would take the y component of r, which is just named y, and multiply it by j hat, which is the unit vector that points in the plus y direction. And it is very common when writing I hat and j hat to not put little dots over them. This has to do with physics notation for differentiation. Plus it just starts looking silly to put a hat over something with a dot. So anyway, this x is the x component of r, y is the y component of r. We do not write r sub x and r sub y like we do for all other components. So we can, again, just follow through in the same idea. We can define displacement to be the change in position. So this will be r2 minus r1. But now the difference is instead of it being unit vectors, instead of it being in 1 dimension, just either be an x or a y value, they are vectors. But it turns out, just to kind of follow the logic through here for displacement, let's do it like this. There we go. It turns out if we follow this through, the r2 we would be writing as x2 I hat plus y2 j hat. And we'd be subtracting from that x1 I hat plus y1 j hat. So what are we doing here? What we're doing here is when we add when we subtract, we will be doing it slotwise like we were doing before. So this would be the same thing as x2 minus x1 times I hat. So x2 I hat minus x1 I hat, grouping the terms with the I hat. And similarly, group the terms with the j hat to get y2 minus y1 j hat, which is what we saw before. Now, what this means is that, say for velocity, if you remember velocity, and we still use the symbol v for velocity, velocity was defined to be the time derivative of position. And if you haven't seen derivatives yet, that's fine. Remember, this is what we were talking about before. This is the limit of a sequence of average velocities as the time intervals get ever smaller. So this will be delta r over delta t. Now, the big idea here is that when I take my differences, I'm only subtracting x components off of each other, and I'm only subtracting y components off of each other. So what this means is that my differentiation, or this limit taking process, however you want to think about it, distributes across the position vector. So I can write this as dx dt times I hat plus dy dt times j hat, but that is the same thing as v sub x. That's the same thing as v sub y. So we can write that as vx times I hat plus v sub y times j hat. And since we got acceleration by the exact same kind of argument, so remember that was defined to be the derivative of velocity with respect to time, which again be the same deal here. This would be a limit as time intervals go to 0 of changes in velocity with respect to time. The exact same logic happens. We're only going to be subtracting y components off of each other, and we're only going to be subtracting x components off of each other. There's going to be no mixing. So this is the same difference as saying dv dt I hat plus dv x dt I hat and dv y dt j hat. So we can write that as the x component of the acceleration times I hat plus the y component of acceleration times j hat. Okay, so this is super duper convenient. What this is going to mean going forward when we start trying to do this analytically is we'll be able to separately treat the x and y components as basically two decoupled one-dimensional motion problems. But before we go there, I think it's good to build an intuition for how velocity and acceleration can relate to each other, going back to our motion diagrams and vectors. So let's think about a situation, say, where we're going around a corner, but now as we go around the corner, we're speeding up. So say something like that. Let's say I'm interested in knowing the acceleration vector right at that point right there. Well, I can get the displacement vector from here to here. So we will call that delta r initial. And I can get the displacement vector from here to there. We will call that one delta r final. And the velocity vectors will point the same way and will be proportional to each other because we're taking equal time intervals in our motion diagram. So we can go ahead and write our velocity vector. So we'll just off to the side, I can write a matching velocity vector, say v initial, like that, and a corresponding v final, like that, pointing the same way, and I tried to keep the lengths proportional. All right. So now to find the acceleration, I can go ahead and take the same logic as before and say that on average, the acceleration will be the change in velocity with respect to time. So this will be v final minus v initial over the time interval. And if I want to find the instantaneous velocity, I would have to imagine a sequence of motion diagrams with ever smaller time intervals and ever finer separations. But this will at least give me a good approximation to the acceleration at this point. So to do that, let's go ahead and we'll subtract these. Let's go use the tail to head approach here. So I'm going to go ahead and make a copy of this. Copy, paste. Yeah, that's pretty good. And we'll make a copy of this. Copy, paste. But keep in mind, what I need is not v initial, but negative v initial. So the way I'm going to get my negative v initial is to flip it. Like that. There, that makes negative v initial. And now I'm going to add it to my negative v initial to my v final. Pardon me a second there. So I'm going to add my negative v initial to my v final by the tail to head rule to get my delta v. So this right here by the tail to head rule would be my delta v, like so. And then my acceleration will be proportional to my delta v pointing in the same direction, because multiplying by 1 over delta t is just multiplying by a positive scalar. So there's my acceleration. Now, here's the thing. Let me go ahead and make a copy of my acceleration. Copy, paste. If I go back, put it where it is here, you'll notice it doesn't point in any particular direction. A particular special direction, I should say. It's not aligned with the delta r initial, it's not aligned with delta r final, it's not tangent to the trajectory. And what we're going to see is that the piece of the acceleration that is tangent to the trajectory, parallel, is going to be responsible for the change in the speed, but the inward pointing piece of it is actually responsible for it changing direction. And so even if you move at a constant speed, if you're going around a corner, the velocity is changing. You're changing the direction of the velocity, but that's still a change. And so that means you are accelerating. Now, if we do follow this little bit through right here, we will get that if I make these intervals ever smaller and smaller and smaller, I will get that the velocity will always be tangent to the instantaneous velocity will always be tangent to the trajectory. Instantaneous velocity is tangent to the trajectory. But, as we just saw, the acceleration can point any which way. Say in different directions. Okay. Now, in the next video, what we're going to do is go back to realizing that when we differentiate velocity, we're just doing the when we get the velocity, we're just looking at taking derivatives of x separately from y, and same with acceleration. And we'll take that to look to analyze situations where the acceleration is constant both in magnitude and direction. So I'll catch you over in the next video.